Hello everyone and welcome. Today we're going to continue our very important topic, which is energy transformation. And today we're going to be talking about conservation of energy in a horizontally moving spring. Now, let's look at this simple spring. Let's say this spring in this condition right now, it's at its normal length. In other words, it's neither stretched or compressed. It's at rest. So this moment, this second right now, it doesn't have any type of energy inside it. Now imagine that we push this spring or we compress this spring to a certain distance. Let's call this distance negative x or x. It doesn't really matter. Now imagine that we stored energy in this spring, and we know that the energy stored in a spring is called the elastic potential energy. So in this moment right now, it's storing elastic potential energy. Is it moving? No, it's not moving. It only stores elastic potential energy. So let's study it at location A. The spring is compressed at a distance x, which causes elastic potential energy to be stored. The kinetic energy is zero since the spring is not moving. Now, if we want to study the mechanical energy of this spring, we will say that the mechanical energy is the summation of all forms of potential energy plus kinetic energy. So let's call it mechanical energy at location A. It's going to be equal to the potential energy plus the kinetic energy. And since it's not moving, we do not have any kinetic energy, so we will only have potential energy at location A. But what type of potential energy do we have? We have the elastic potential energy. And as a quick reminder, the elastic potential energy is equal to half kx squared, as a quick reminder, where k is the spring's constant and x is the distance the object was compressed. So again, at point A, it will only have elastic potential energy inside it. Now imagine that we let it go. It will start moving. Now, let's say that we took a picture of the spring when it reached to location B, where it is almost, or let's say, where it is at the same location it started from. Now, this dashed line is an indication of the location the spring started from, where we said that it wasn't compressed or stretched. So in this case now, it's in its original length. Okay? It's neither stretched or compressed, but it is moving. So we can say that at location B, the elastic potential energy is transformed into kinetic energy, and the spring is at its highest speed. So the spring will be at its highest speed when it reaches the length where it is not stretched or compressed anymore. No more elastic potential energy is stored in the spring since it is in its original length. If we want to look at this energy bar chart, we can see that the potential energy this time is equal to zero, but it has its full speed and full kinetic energy. Now, it won't stop moving at this point. It will stretch in the other direction. Let's call this point number C. It will stretch. It will continue moving. Now, if we want to study the energy at location C, we're going to say that there will be no more kinetic energy when it reaches its full length. At a certain point, it will stop and it will go back in the other direction. In this moment, there is no velocity. It's not moving, but the spring is stretched. So therefore, we will have elastic potential energy again. So the kinetic energy is now transformed again into elastic potential energy. No more kinetic energy is present. Therefore, the speed is now zero. If we want to study the mechanical energy at location B, we're going to say that the mechanical energy at location B is the potential energy plus the kinetic energy. And we know that the spring is not stretched or compressed, so we do not have potential energy. So it will be simply only the kinetic energy at location B. And if you want to study the mechanical energy at location C, we're going to say that it is equal to the potential energy plus the kinetic energy at location C. But since it's not moving, there is no kinetic energy anymore, so it's only the potential energy at location C. So what's happening simply is that we compress the spring, we store the elastic energy in it. We let it go, the energy or the elastic energy stored in the spring is going to be transformed into kinetic energy, and it will continue moving. So at a certain point, it will lose all its kinetic energy again, and it will gain potential energy. Now, if there is no energy losses, in other words, there's no air friction, and there's another term that we use with springs called damping. Damping is actually like the internal friction between the molecules of the spring itself. This also causes energy losses. Let's imagine that we have no damping and we have no friction in any other way. In this case, the spring will continue moving back and forth perpetually. In other words, it will keep going back and forth forever, which is only theoretical because there's no spring that has no damping. Okay, even if we were able to get rid of the friction between the object and the air, we cannot get rid of the damping between the molecules of the spring itself, or the friction between the molecules of the spring itself, which we call damping. Let's make sure that everything is clear and take this simple example. If the spring was pushed initially a distance of 0.05 and the spring's constant is 15 newtons per meter and the mass of the spring was 0.1 kilograms, find the potential energy the spring has stored. Okay, I could say that the potential energy, or the elastic potential energy in this case, is going to be equal to half kx squared. And we can say that it's equal to half multiplied by the spring's constant, which is given in the example as 50, multiplied by x. X is the change in the length of the spring, and it said that the change in the length of the spring is equal to 0.05 meters, so we will multiply it by 0.05, and this is squared. Do not forget the squared. This will give us an answer equal to 0.0625 joules. Okay, now remember that this is the spring. Let's imagine that this is our spring and it has been compressed from its original length. Let's imagine that this is its original length at a distance equal to 0.05. We can say that the mechanical energy at this point right here, it's going to be equal to the elastic energy. In other words, the mechanical energy, let's call this location A. The mechanical energy at location A is going to be equal to 0.0625 joules. Let's go for the second question. Find the maximum kinetic energy the spring can achieve. We already mentioned that the spring can achieve its maximum kinetic energy when it goes back to its original length. So this is the dotted line. This is the original length of the spring. So we know that it will reach its full kinetic energy when it reaches this point again. Let's call this location B. We know that the mechanical energy at location B, because it's back at its original length, we will not have any potential energy, but we will only have kinetic energy at location B. And we know that mechanical energy is conserved. So I can say that the mechanical energy at B is equal to the mechanical energy at A. So I'm going to say that the mechanical energy at this location, let's call it location B, is equal to the kinetic energy at location B. And I know that the mechanical energy at location B is equal to the mechanical energy at location A. So I can say that 0.0625 is equal to the kinetic energy at location B, which is the maximum energy. In other words, when all the potential energy is transformed to kinetic energy, this will be the maximum kinetic energy. And this happens when the spring is at its original length again, when it lost all its potential energy and transformed it into kinetic energy. Now, part 3, find the maximum speed the spring can achieve, or the maximum velocity. I know that the kinetic energy is equal to half mv squared. And from the previous example, we found the maximum kinetic energy. The maximum kinetic energy occurred at the location B, which was equal to 0.0625 joules. This will be equal to half multiplied by the mass, which is 0.1, multiplied by the velocity squared. So what I can do right now, this will be equal to 0.0625 is equal to 0.05 v squared. I want to get rid of the 0.05, so I'll divide both sides by 0.05. And I can say now that v squared is equal to 0.0625 divided by 0.05 is equal to 1.25. And I want v, not v squared, so I will take square root for both sides. And in this case, v will be equal to 1.11 meters per second. So I found the maximum velocity the object can achieve. Now find the spring speed when the length of compression becomes 0.025. Now this is the object when it was compressed at a distance equal to 0.05. This is the original length. 0.05. In this case, we said we have no kinetic energy. We only have potential energy. Now, I'm asking you to find the speed of the object at a point where it is right here, right now, and the distance became 0.025. In other words, it is still moving and it is still compressed. It's compressed by a distance equal to 0.025. Well, we know that the mechanical energy is conserved. So let's call this location E. The mechanical energy at this point at E is going to be equal to the kinetic energy at E and the elastic potential energy at location E. Okay, I can start with finding the elastic potential energy at location E. I can say that, let's rewrite the equation here. The mechanical energy at location E is going to be equal to the kinetic energy at location E plus the elastic potential energy at location E. Okay, now the mechanical energy at E. Can I find the mechanical energy at E? Well, actually you can, because we know that energy is conserved. And we already found, we called this location A. We already found that the mechanical energy at location A was equal to the elastic potential energy, which we found was 0.0625. So I already know the mechanical energy at location E, so I can just substitute it right now. 0.0625 is equal to the kinetic energy plus the potential energy at when it's compressed at a distance 0.025. So I can just simply find it, which is half multiplied by K, which is 50, multiplied by the distance 0.025 squared. Now, this will take us to 0.0625. It's equal to the kinetic energy at location E plus 0.015. This is, when I multiply all these numbers together, I will get 0.015. Now let's continue solving this problem right here. I can say that the kinetic energy right now, I will subtract 0.015 from both sides. It will be equal to 0.046. Now this is the kinetic energy, but it's not asking for the kinetic energy, it's asking for the speed or the velocity. So again, half mv squared, which is the equation of the kinetic energy, is equal to 0.046. Now, half multiplied by the mass, which is 0.1, multiplied by the velocity squared is equal to 0.046. Let's continue solving the problem right here. 0.05 v squared is equal to 0.046. Now, by dividing both sides by 0.05 to get rid of it, 0.05, I will get that v squared is equal to 0.9. But I want v, not v squared, so I will take square root for both sides, and I will get that v is equal to 0.95 meters per second. So I found the velocity or the speed of the spring when it was compressed at a distance equal to 0.025. Actually, you can find the potential energy, the kinetic energy at any location if you have enough info, just by using the idea of energy conservation and that the mechanical energy is conserved always. Stay tuned in the next video. We will be covering how to apply the energy transformation concept and the conservation of energy on a spring, but this time when it's moving vertically. Think about it yourself. What's going to change in the spring's energy when it's moving up and down instead of moving to the left and right? And we will be answering this question in the next video. Stay tuned.